Okay, so in this video we are going to look at some of the linear algebra background that's needed to understand some of the projection methods. And in this week in general, we're going to be looking at an introduction to projection methods and then actually how we can implement them. We're going to look at that next week. So there's an underlying approximation problem that's happening that we can sort of think about in a couple of different ways. So let me just mention that now. So the space we're going to be dealing with, I'm not going to write it down, is Rn, and everything is going to happen inside of Rn. And we're thinking about n as being a big number, like that's the side of the matrix. We have an n by n matrix. So n, we want to think about as being big. So let V be an m-dimensional Let V be an m-dimensional subspace in Rn. And, okay, now every subspace has a basis. That's just sort of the definition of being a subspace. And by the Gram-Schmidt process, we can assume that it has an orthonormal basis. And that's going to be helpful for some stuff that we want to prove in just a little bit. With an orthonormal basis, V1 through Vn. Okay, so these vectors are pairwise orthogonal to each other, and they have unit length. And when we say orthogonal, it could be with respect to any inner product, and we need to have that generality. So not just with respect to the standard inner product, but with respect to any inner product. Or we can find a basis that is orthonormal with respect to, given an inner product, we can find a basis that is orthonormal. Okay, so let V be an m-dimensional space with an orthonormal basis. We can always complete this. In other words, add vectors to it. We can complete this to an orthonormal basis for Rn. We can complete this to get an orthonormal basis for Rn. So we're going to have our vectors v1 through vm, and then I'm going to add the other vectors w1. I'm going to call it wl. These are the vectors like m plus l is equal to n. These are these vectors right here, v1 through vn. Those are vectors for these are a basis, orthonormal basis for the vector space V. Let me just write that. These are vectors for the a basis for the vector space V. And then these vectors right here, these W vectors right here, well, they're a basis for everything else, but that everything else has a name. It's called V-perp. It's the orthogonal complement of V. So this is a basis for V. This is the basis for the orthogonal complement. Why do we call it the orthogonal complement? Well, it's called orthogonal because everything in this vector space here, if I look at the linear span of the vectors W1 through WL, they are orthogonal to all of these vectors here. So this is the orthogonal complement to this. It's called complement because when you put all of them together, you get the entire space. And for this reason, sometimes you will see that people will write Rn as the direct sum of these two spaces here. Now what this means, as we'll see in just a minute, any vector can be written as a vector in V and a vector in V-perp. Okay. So let's say we are given, you know what, let's try a different color here. I don't know how well this is going to work, but I want to see. Should have tested before, but I didn't. Okay. Let me see how well that shows up. Okay. Given a vector B in Rn, we want to find the vector V in the subspace V that minimizes v minus b. Okay, and again, this could be any norm. It could be any norm at all. We want to typically think about it as being a norm induced by an inner product, though. Okay. So in other words, what we're doing is we want to find the vector in V that best approximates B. So in other words, if we can only take vectors in V, we want to find that vector that gives us the closest thing to B. So here's how we can do that. So, and again, we're assuming that this norm is given by an inner product. So note that V can be written in the following form. The sum k equals 1 to m, I'll say ck vk. Okay, we don't know if V is just a generic vector, we don't know what the ck's are, but we know that if V is in the subspace V, it can be written in this form. And then B can be written in the following form. K equals 1 to n. I'm going to call these first set bk with a superscript of 1 vk plus the sum k equals 1 to l, and then I'm going to have bk with a 2 times wk like this. Okay, so this is just based on the fact that we can write B. I mean that the V's through W's are a basis for Rn. V is in Rn, and so there are coefficients, the bk1s and the bk2s, so such that B is equal to this. Okay, and since it's an orthonormal basis, we know that like bk1 is the inner product of B with vk, and bk2 is the inner product of B with wk. That's not so important right now, though. All right, so now what we want to do is we just want to measure the difference between V and B. So we're going to do this by looking at the inner product. V minus B. We're going to look at that inner product. Okay, so that is actually minimizing the square of this. Okay, because this right here is V minus B squared, the norm of V minus B squared. So we're actually minimizing the square of that, but of course it gives us the same solution. Okay, so what's going to happen here, and this is an exercise for you guys to do. When you do this inner product, notice what happens. So the VKs, when you inner product with the WKs, that's all going to be 0 because all of the WKs are orthogonal to all of the VKs. If you do a VK with VK, what's going to happen there is when the sum, when VK with VK is equal to 0, but VK with any other, VJ, where K and J are not equal to 0, is going to be 0. So VK with VK is 1, VK with another VJ is going to be equal to 0. Okay, and so actually replace V with this, replace B with that, here and here, and do this computation, and you will see that it is going to be equal to the sum K equals 1 to N CK minus BK1 squared plus the sum K equals 1 to L BK2 and that squared. Okay, now here's the thing. Our goal is to find the CKs that minimize this. Well, this is a sum of non-negative terms, so it's a non-negative sum. Same thing here, that's a sum of non-negative terms, so it's a non-negative sum. So if I want to find the CKs that minimize this, it's going to be where this sum is equal to 0. In other words, where CK is equal to BK1, and as I mentioned, we know this is just going to be the inner product of B with VK like this. Okay. So we want to find the V that minimizes this, and we have a formula here for it. And what we know is true is that given a B and Rn, we want to find the V and V that minimizes V minus B, and the solution the solution is v hat is going to be equal to the sum k equals 1 to n b comma vk and then vk. Like this. Okay, so note that if we look at b minus v hat, what do we get? Well, all we're left with is the sum k equals 1 to L bk2s times wk. But every element of wk, so all of these vectors wk, are orthogonal to all of these v vectors. In other words, each one of these wk vectors is orthogonal to the space v, and so this vector is orthogonal to v. So another way that we can view the solution is going to be find the v such that find the v hat, I should say. Find the v hat such that v hat minus b is orthogonal to v. Both of those are going to be the minimizer for this problem here. If you're just looking at vectors in v, they're both going to be the minimizer. Not that they're both going to be the minimizer, they're like the same thing. Okay, they're the same solution, they're the same vector, just different ways of describing the vector. Okay, so this is going to be very important to what we are going to be doing in this class in the projection method, because this v hat is called the projection of b onto the subspace v. And we need to know that it satisfies all of these very nice projection properties to be able to prove that some of the things work the way that we claim they work. Okay, now I think for this video that is all I want to say. Let me say one more thing. I think it's going to be better if I say it. I had initially planned to say it in this video, so I'm going to keep and say it in this video. Okay. So oftentimes the way this sort of thing gets applied is in the following situation. I'm going to go with a different color, maybe a slightly lighter color. So this idea gets applied in the following situation. So we want to do something like solve an equation mx equals b. Now, the idea in the framework that I'm working in now is that M is going to be a matrix with fewer columns than rows. So it's like a skinny matrix. So in other words, well, just in general, for there to be a solution to this equation, B has to lie in the column space of M. Okay, so often B has to lie in the column space of M. Not often, all the time, B has to lie in the column space of M for there to be a solution here. But oftentimes, that's when I meant to say often, oftentimes M is going to be a matrix that's way longer, right? It's going to be a matrix that's way longer, and so if it's way longer than it is wide, then what does this mean? It means the columns of M have large dimension, but there's only a few of them, comparatively speaking. So then what this means is that it's unlikely that a vector is going to lie in the column space of M, because the dimension of the column space of M is just equal to the number of columns of M, and if that's a skinny matrix, then that's going to be much smaller than the dimension of B. Okay, so then the next best thing that we can do is minimize and x, the dimension of x is going to be equal to the number of columns of M. So find x that minimizes we want to find an x that minimizes mx minus b, and again, relative to some some norm induced by some inner product. You can think the standard Euclidean norms and stuff like that, but we really want to think in the generality of this being a norm induced by generic inner product, because that's how we're going to apply it. Okay, so find x that minimizes this. But as x ranges through its space, that is R of, Rm, where m is the number of columns of m. As x ranges through its space, m times x, notice what we're doing. For every vector x, we're forming a linear combination of the columns of m. So if we look at all of the x's that we could put there, as x ranges through its space, mx ranges through the column space, I'm going to call this V, suggestively, through the subspace V, which I'm calling the column space of M. Again, because for every x, we get a different linear combination of the columns of M, and we can do all of those linear combinations, and so we're going to get the column space of M. Okay, so then what this problem becomes is we want to find a vector in the column space of V that minimizes, we want to find a vector in V that minimizes this. Okay, in other words, we want to find a vector x such that mx minus b is orthogonal to the columns of M. Okay, so again, we want this residual vector to be orthogonal to the space spanned by the columns of M. That's exactly what we're saying here. That's exactly what this says. Okay, so once again, why do we want that? Well, we saw before that if we have a subspace V, and we want to find a little v in V that best approximates B, we want to find the v hat so that v hat minus b is orthogonal to b, or orthogonal to v. But now this represents the v's that we're looking at, and v is a column space of M. Okay, so what we want to do then is we want to find a vector x so that, again, this is our v hat, so that v hat minus b, or mx minus b, is equal to little m. That is the goal of what we're trying to do here. Okay, that's another way to sort of say if we can't solve this problem, the backup is to solve this minimization problem, and another way to say this minimization problem is this right here. Okay, now with those two pieces of information, or with that information from this video, we can now look at some of the basic projection methods, but that I'm going to save for the following videos.